Good morning, or good afternoon. My name is Rhea Malhotra, and I'm a junior from Moravian Academy in Bethlehem, Pennsylvania. And today I'm excited to present my research regarding my second year of work using optical coherence tomography to study cardiovascular disease in Drosophila melanogaster. And this was for the purpose of analyzing the biochemical effects of hypoglycemic agents on diabetes-induced cardiomyopathy in vivo. So to understand the scope of this study, we actually have to look back at the conclusions I arrived at last year. So the goal of my study last year was to develop a accurate, cost-effective, non-radiation-based approach to live 3D imaging of cardiac physiology for drug development. So the goal of this was to enhance cardiac imaging of physiology to understand how different drugs can influence factors like heart rate, heart area, heart wall thickness, and ejection fraction, which is like the volume output per beat. I did this by understanding how different antiarrhythmic drugs, namely class 1, 3, and 4 antiarrhythmics blocking sodium, potassium, and calcium channels, affected these physiological factors, and they were measured on a platform on Python and Matlab that I coded for real-time data. Ultimately, I found that this optical coherence tomography system using lasers was an effective means of real-time analysis of cardiac physiology, and that it can be used in a healthy model of disease, So currently, the pharmaceutical industry is actually largely inefficient, in that it takes over $2.5 billion to develop a single drug on average. It can take upwards of 20,000 people per clinical trial and almost a decade of time in testing. My idea proposes that a fruit fly and OCT system can actually be an intermediate phase between in vitro and in vivo testing in mammals, saving time, energy, and expense for researchers. So the main transition phase between my last year's study and this year's study was moving from a healthy model of disease, in which I used just a healthy fruit fly and altered physiology using antiarrhythmics, was now to actually move into a disease model. So I actually worked on inducing diabetes in Drosophila melanogaster, or the common fruit fly. And I was using hypoglycemic agents, or different drugs that actually lower blood glucose levels, to try and treat this induced condition in the model organism. So diabetes mellitus is currently the 7th leading cause of death worldwide. 30.3 million Americans are afflicted with the condition, and 1.5 million are diagnosed every year. It's caused by the mismanagement of blood glucose due to the improper regulation of the hormone insulin. So there is a strong known comorbidity between diabetes mellitus and cardiovascular disease, seeing as heart conditions are the #1 cause of mortality in diabetics. Cardiomyopathy has also been known to increase as a result of the chronic high glucose associated with diabetes. So my new study worked on actually inducing diabetes in the fruit fly and being able to treat them with different hypoglycemic agents, namely insulin, metformin, sitagliptin, and glipizide, to understand how these drugs for diabetes can actually regress the effects of cardiac hypertrophy, or the gradual thickening of the heart wall. And I measured this through heart wall thickness through optical coherence tomography. My hypothesis was that all but insulin would actually lead to a decrease of hypertrophy, so they would actually be able to regress the progression of cardiovascular disease. And this was based on existing research regarding insulin. So optical coherence tomography itself was the laser imaging system utilized to harness my data. So OCT functions based off of the backscattering of photons off of a sample substrate, and it's unique in the sense that it's only been developed in the past 5 to 10 years or so, and in this time in humans it's only ever been used in retinal imaging. So this study was somewhat novel in the sense that it was the first to ever actually use OCT for this purpose and use Drosophila for drug development, which has never been done before. So Drosophila melanogaster were the model organisms for this study, also known as the common fruit fly. They were used because they can be tested in large populations in a relatively short time period, and although they do have a single-chambered heart and humans have a 4-chambered heart, despite this physiological disparity, the electrophysiology and voltage-gated ion channels of the heart wall are actually remarkably similar. So the mechanisms by which the heart contracts can actually be compatible for drug testing. So the variables in the study that were manipulated, or the independent variables, was the drug type being tested. So this included the 4 hypoglycemic agents, insulin, sitagliptin, metformin, and glipizide, as well as 2 control groups. So a diabetic control, which was just treated with the high glucose diet, as well as a healthy control, which was treated with normal fly feed. The 4 hypoglycemic agent trials were first treated with the high glucose diet, and then 4 days later treated with the drug itself. The procedure by which the concentrations of the drug were identified was based off of a methodology that I optimized in my previous study with antiarrhythmic agents, using 0.1% of normal human dosage diluted in regular fly feed. So this caused variation depending on the normal human dosage. The dependent variable, or the factor that was measured, was heart wall thickness, which is indicative of hypertrophy, a type of cardiomyopathy. And the constant variables were held for utmost accuracy in results. The first stage of my testing was drug delivery, so actually being able to induce diabetes in these flies and then treating them with the hypoglycemic agents. As I said, 0.1% of the normal human dosage was diluted in normal fly feed, and this oral delivery was optimized last year. After these samples were constructed, they were imaged under normal optical coherence tomography protocol, and this was then processed through my Python and Matlab codes. And these would be some of the M-mode images or slices that were actually generated. So for example, this would be one of the videos that I could get in real time with my system. So this is actually a cross-section of what a beating fly heart looks like. And using my system, I can generate real-time quantitative data regarding how the heart actually beats. And with a Matlab stitch compilation file, you can actually put these different cross-sections together to generate what the 3-dimensional fly looks like in 3D. So what this allowed me to understand from a quantitative perspective was that developmentally from larva to adult, there is regular aging with heart action, which we see in humans, as there is an increase in heart wall thickness from larva to adult. So the systolic data, or when the heart wall was actually in contraction, showed that between the null control and the diabetic control, there was actually an increase in heart wall thickness, which is what we expect to see in humans. And then from the 4 hypoglycemic trials, we actually were able to identify a significant decrease in heart wall thickness. So that supported the hypothesis that these hypoglycemic agents would be able to regress the effects of diabetes-induced cardiomyopathy. And similar effects were found with the diastolic or the relaxed measurements. Relatively, I found that systolic values were much higher than diastolic values, and with a t-test, I found that these data sets were statistically significant. Ultimately, I found that insulin, metformin, and glipizide insulin, sitagliptin, and glipizide resulted in 20 to 25% decrease in cardiac hypertrophy as opposed to a normal diabetic control, showing that not only can these hypoglycemic agents reduce the effects of diabetes on a patient, but they can also help prevent the onset of cardiovascular disease. Currently, the #1 cause of death worldwide is cardiovascular disease. And with better drug development methods for creating novel therapies for this condition and diabetes alike, 25% of deaths globally could be prevented. So progressing my research on optical coherence tomography and drug development can help target this issue. Specifically for diabetes, this would help in creating novel drug types with relatively little expense associated with drug development. And currently, I continue to work on different hypoglycemic agents and also utilizing this technology in compatibility with Optogenetics. These are some of the sources I used for my study, and thank you for your time and attention. Do you have any questions?
I have a couple questions for you.
Of course.
Did you baseline the size of the hearts before you induced diabetes to see, like you said, it was reduced 25%? Did it return to where it started, or did you ever start with a baseline with the heart wall?
Oh, you mean as in like the same sample? I didn't do that, but I compared it to a control group because if I had measured it before, there would have been like a developmental effect associated with the heart wall thickness. Because in the span it took me to treat the fly with diabetes and then also with the hypoglycemic agent, that 1 week of progression would have drastically altered the values.
And also, did you look at the side effects of doing the different drugs and reversing it? Did it have any other side effects of using those drugs?
In the scope of this study, I only identified cardiac physiology, but in the future, I'm actually looking at understanding this from a histological perspective. So actually, I'm going in and cutting slices of the fly heart, but I need new equipment for that, so I have to find a way.
Where are you doing all this?
So I just initially started at shadowing a lot of PhD students at a university lab at Lehigh University near where I live. And then after 6 months of just watching them use the system, I proposed this project, and now I just work under their supervision independently.
They're letting you use their labs and work in their labs.
Yes, so their lab actually it just works on enhancing the laser itself, but the flies and everything, that's all my independent study.
Were there any surprises during your study? And I don't know anything about surprises about the fruit flies?
Well, with the fruit flies, it's actually kind of funny because I'm really afraid of bugs. So whenever I was imaging them, the worst part was if they flew away or anything. But from actually one of the biggest challenges with coding the Matlab and Python software to actually being able to get accurate results regarding heart rate and heart area, and that taught me a lot about coding itself because I didn't have much experience in that before.
Great, thank you very much.
Thank you very much.
Thank you.